네, 그럼 지금부터 첫 번째 특별 강연 시작하겠습니다. 세션 중에 질의사항이 있으신 분은요, 좌석에 비치된 질문지에 궁금하신 점 기재하셔서 진행 요원에게 전달해 주시면 되겠습니다. 자, 전 발표자 소개해 드리겠습니다. 발표는 프라딥 두베이 인텔 병렬컴퓨팅랩 소장님께서 궁극의 학습 기계를 찾아서, 굉장히 주제 흥미롭죠. 이 주제를 가지고 강연을 펼쳐 주시겠습니다. 자, 진행과 대담은 한국연구재단 정민근 이사장님께서 수고해 주시겠습니다. 자, 두 분을 단상 위로 모시겠습니다. 네, 여러분 큰 박수 부탁드릴게요. 네, 그럼 저는 마이크를 이사장님께 넘겨드리겠습니다. 정민근 이사장님, 진행 부탁드립니다.
네, 감사합니다. 오늘 첫 번째 특별 강연 발표해 주실 프라딥 두베이 박사는 인도 버라 인스티튜트 오브 테크놀로지에서 전자통신공학 학사학위를, 유니버시티 오브 매사추세츠 앰허스트에서 전기공학 석사학위를, 그리고 퍼듀 유니버시티에서 전기공학 박사학위를 취득했습니다. 1991년부터 2001년까지 IBM의 TJ 왓슨 연구센터에 참여했으며 2003년부터 인텔사의 펠로우이자 인텔 병렬컴퓨팅랩 소장을 맡고 있습니다. 듀베 박사는 IBM 파워 PC와 인텔의 고성능 컴퓨팅을 위한 새로운 MIC 아키텍처 등 다양한 프로세서 성능 개선을 위한 연구 개발에 참여해 오셨습니다. 2012년에 인텔 어치먼트 상을 받았으며 2001년에는 멀티미디어 처리 아키텍처 개발에 기여한 공로로 국제 전기전자공학회인 IEEE 펠로우로 선정되기도 했습니다. 오늘 듀베이 박사님께서 발표하시는 주제는 The Quest for the Ultimate Learning Machine입니다. 최근 화두가 되고 있는 인공지능의 핵심 기술인 딥러닝, 그리고 궁극적으로 사람을 대신하여 스스로 학습 가능한 컴퓨팅 모델에 대해 약 한 30분 내지 35분 동안 강연을 하시고 15분의 질의응답 시간을 갖도록 하겠습니다. 듀베이 박사님, Dr. 듀베이.
Good morning. I, the human race, we are very ambitious people. And this talk is about one such ambition. And the ambition is to build or create something that's better than its creator. And you can imagine it's like some would argue whether it's even possible. But since no one has proven that to be impossible, our quest goes on. And more importantly, I hope you'll realize through this talk that even if we fail in this ambitious mission, we would still have actually solved some of the very hard problems of our society. And this talk is primarily about taking computing to actually solving social problems, a whole class of problems that today it does not address. So with that, let me begin. And we, in our lab, in our research, have been doing parallel computing for a long time. This is what I did at IBM also, and I continue that work at Intel. Parallel computing, which is only needed when you have a lot of compute to deal with or a lot of compute to deliver, has traditionally is how we have been solving hard problems. But before we go there, let's look at how human beings interface to a computer, right? We have a problem in our mind, and we want computers to solve it. Like previous speaker was saying, we typically program things. We explain that problem somehow to the computer. Computer figures it out, returns the answer back, right? At the end user level, we can only figure out if the computer has really gotten that problem right or wrong by looking at its one of two kinds of outputs. One is called mining, which means can the computer go back in the archives and find similar things. So I'll use an example. If I show a flower to a computer, right, I don't exactly know how computer is going to model that flower, or like that apple in that example, in the trash can example, or tomato. The computer, but doesn't matter, if the computer can go and find similar objects, then it must have the right model of that thing that the problem or object or event I had in my head. Similarly, if the computer really understands that event or the object, it should be able to create similar things. It should be able to synthesize or simulate in the future. So its ability to go back in time and find similar things, like when we typically Google things, or its ability to go in the future and predict something, or simulate or synthesize such a flower if it doesn't exist, that's how we know that the computer has a good understanding of it, right? So end user can only judge the goodness of a computer's understanding of a problem by one of those two ways, mining or synthesis. So if computer really understands what is a certain object or an event, object like a tomato, event like a trading opportunity, its goodness of that understanding can be judged if it can find similar instances or create similar instances and answer what-if questions, futuristic questions. If it can predict whether it's going to rain or not, it must understand what it is to model a rain or have weather prediction, right? So these three core components of an application, namely how do you really recognize something and how do you then find similar instances or create or simulate future instances, what is it made up of? In schools, when we teach them, there are all kinds of deeper fields that are underneath it, behind it, the computer science algorithms like the last speaker was saying. Now, the tragedy, however, is that these things are not taught in a loop or not taught together even in computer science classes. The database guy doesn't talk to graphics guy, they don't talk to the speech guys, they're all different disciplines, even in schools, right? So what is really needed here is now to be able to close this loop so that we can actually be solving these problems in a loop. And that's how we can solve newer and newer problems. Let me now go back to where the crux of the problem is. It's in this ability to model things, the quote unquote, the recognition part of it. Computer's ability today is very, very limited. So most of the cycles are spent in mining and synthesis. Very little cycles are spent in actually understanding or modeling complex objects. Okay? Now, why is that the case? Because so far we have been limited to what you see on your right, the inside-out way of doing things. Meaning we are limited to only be able to process in computer things for which we have a nice formulation. It could be Schrodinger equation, Newton's equation, Navier-Stokes, things which have nice formulations, meaning some smart guy, some scientist gave us the right formulation. We throw a lot of compute flops to solve them, to solve those equations. But there is 99.9% of the problems in the world are not lucky enough to have a formulation like the one you see there. They are not lucky enough to have a guy like Newton or Einstein. So those are the problems on the left side, the outside-in problems, where you have to come from outside, and just by looking at the output, you somehow try to guess what could be going on, what could be a good way to represent or model that, right? That's where we are now mostly focused, because this is how we can handle 99% of the problems that so far are out of reach for compute. Now, why have we not done this so far? Very simple. The theory has been known for a long time, but we did not have enough data or enough compute to have a reasonable confidence in the reverse engineered representation or model of the problem, okay? Which is what is changing now. How? Because now we have a lot of data and a lot of compute. And you can clearly see through this example, for example, video has grown, skyrocketed. Clearly the eyeballs in the world have not grown. World population has not grown like this. So the only way this amount of data can ever be analyzed is by computers, is by machines, not by humans. Now, therefore, what is happening is edge devices, as the digitization takes place, edge devices are sensing, and that's where humans come to interface the computing, and at the back end, large amount of data is being collected. That's the quote unquote big data servers. And the model building or understanding can only be done at the back end because that's the only place you have enough data. Okay? So the only, and it's very, very powerful. It's powerful in the sense that you can imagine that it's the effect of internet. In the past, it was very hard to collect enough data. You can imagine if your computer tried to understand my accent, IBM had such products via voice. A guy like me, my accent, it'll take a lifetime learning for it, right? But now, million people can speak to it with my accent, and they all go to the server. So it's like tossing a coin million times versus tossing million coins at once. So for processes where that stationarity holds, you actually have the power of internet to train it in a second, which would have taken otherwise a lifetime. So if you look at what has happened today, if you add up the flops of top supercomputers and the data centers in the world, you already have beyond exaflop today, where we are, right? There's no single computer with exaflop, but computers already have exaflops. Now, at the same time, you also look at the number of internet bytes that we are generating. It's already crossed zettabyte. So if you look at the ratio of the two, which means for every byte that is put on the internet, we roughly have 10 raised to 4 flops to process to decide whether to throw the byte or put it on the internet, which is not much. Why is it not much? Because look at the rate at which they're growing. Compute is barely doubling every year and a half, but data is doubling more than every year. That difference in rate means that pretty soon you'll not even have one flop to decide whether to throw the byte or keep the byte, which means it's not sustainable. All it means is that the need for compute can only grow. Like I said, human beings are not going to process the data at the rate at which it's being generated. It'll take a lifetime to process, to see a 13 seconds of data that gets generated as a video, for example. So it's all can only be consumed by machines, which means the compute requirements can only skyrocket from here if this approach, the outside-in approach, works. So that's the hard problem. So what does it mean? What has it meant so far that in key cases, we see glimpse of how the kind of problems we can now solve. And these things get a lot of press, as you can imagine, right? With applying this amount of compute on this amount of data, we are now able to see at least examples where computers are able to beat, machines are able to beat best humans, such as the Jeopardy game, the AlphaGo, Aristotle level 9 champion, and the Google car, and the car, self-driving cars in general. You can see each example here that what is fundamentally happening is with this amount of compute and this amount of data, we are able to finally solve some non-trivial problems. What kind of problems are these? They're not purely computational problems. Let's understand what kind of problems are these. So what's fundamentally happening is the following. There has been a nice division of labor between machines and humans. What is that division of labor? That's what keeps us all employed. The division of labor is computers are the best at number crunching. So no one tries to challenge a machine today, unless you're Shakuntala Devi. You don't challenge a machine for multiplying or factorizing numbers. At the same time, humans are the ones that are making decisions at every level. Whether it's a matter of deciding the grade of his kid in school, where to build a hospital, whether a guy has a heart attack or just gas problems, medicines, schools, where to farm, or who to put in jail, who's a bad guy, who's a good guy. You may be getting stock exchange data from every stock exchange on the world and on your phone. Still, you're likely to ask your friend, should I buy Intel or sell Intel? Computers do not help you with that simple decision making. They can stream the whole world's data to you, but the decision making is entirely human today. This is the balance. This is the division of labor that is about to be disrupted. Machines are now claiming, no, I can actually do decision making as well. Like you saw, I don't get headaches, I don't have biases, I don't suddenly decide to text. Let me decide things now. This is fundamentally what is going to, this has enormous implications for society, and I'll discuss some of these, but I'm primarily here to discuss the compute implications as to why this is now possible and what does it, and what are we doing to understand this and enable this. So what does this mean? What it means is almost no less radical than the first revolution that took place some time back, Industrial Revolution, right? Which created an efficiency in mechanical efficiency of machines which was unparalleled. And that's how factories happened, right? Mills. Now we are talking about a new revolution of information age where we are actually creating another second generation MELS 2.0, which is an acronym. I coined this acronym. It stands for Machine Intelligence Led Services. Important thing to note here is it's machine intelligence is in the leadership. So unlike human in the leadership and machines helping, machine intelligence for a class of problems are now claiming to be in the leadership. So humans literally take the back seat. That's precisely what is happening in self-driving car, literally, right? Very few people would have ever predicted it will happen at this pace. So these class of services are the ones where machines are actually doing a job better than human, and therefore they have earned the leadership position in that decision making. And the only place it was practiced so far was actually program trading on Wall Street, where machines do the trading, humans later find out whether the trading was done right, whether they got the bid or not. Now, same kind of latency is what is required in self-driving, but it's not just trading. You're now going to kill someone in that millisecond of wrong decision. So it's a much harder real-time decision-making task that machines are signing up for or gearing up to deliver. Now, but let's think, let's go back to the best decision maker of today, the human. Human beings are very good decision maker, but let's realize it's a very complex process. Learning and decision making is very, very complex. And I encourage all of you to read this book, Thinking Fast, Thinking Slow by Professor Daniel Kahneman at Princeton, a Nobel laureate, right? And if you read this book, you'll realize that how complex human decision making is. We don't always do a lot of compute to decide something. In fact, his theory is that we decide something, our system one decides. It's a gut feel decision. And then we rationalize it somehow, okay? So human beings solve this problem not exactly how we would try to solve through brute force compute, very differently. At the same time, it's important to understand because computationally, these problems are NP hard, right? Meaning the complexity is not n raised to something, it's something raised to n, which is very, very different, okay? So what is therefore, other thing to notice about how we solve these problems, that anything that is human services led, where humans are in the lead, the variance in quality is enormous. There's a huge difference between anything humans do when it comes to the quality. There's a huge difference between a terrible singer and the best singer. Terrible player, the best player. Terrible politician, the best politician. Terrible doctor, the best doctor. Terrible teacher, the best teacher. Anything humans do, the output quality is hugely different from worst to best. So the variance is huge. All it means is the machines don't have to beat the very best. It's probably enormous, it's probably an impossible task, even though it gets a lot of press. But even if they can do a better job than the worst, which is much, much easier, still very hard, and slowly begin to rise at the top, they can replace and do a far better and far more predictable job. And what it means is efficiency of many social problems will go up. And all those problems like efficiency of how we teach, efficiency of how we farm, efficiency of how we treat people, all of those problems will see a rise in efficiency if we can now begin to solve those problems. So it also means finally that for us who design machines, it's also time to go and look back at our fundamental model of computing. Why these problems are so hard for us, for the kind of machines we have designed. And let's go back and realize that 70 years back almost, John von Neumann, right, he first came up with the current model of computing by actually analyzing brains, right, actually trying to figure out how we think. This is the ultimate computer. That's how we came up with this split of computing and code and program and memory. That's the quote-unquote von Neumann model. So this model is a model that has served us 70 years. It's probably time to go back and revisit it because clearly there is no such thing as code and memory here. So we are also trying to understand that. So this is about trying to understand humans and trying to understand how they think. It's not, we don't have to literally reproduce it. Remember, to build a plane, we didn't really recreate a bird. It doesn't have a wing, it doesn't flap, but we still, it's be good to understand, even though we're not literally trying to reproduce, we're trying to do something better. So in our research in Intel, we are looking at this problem at all three levels. At the level of science, meaning at the level of how people think, how humans think. And we have a collaboration, and I'll get to some details in each case. And secondly, at the level of computer science, which would be most of my talk, the algorithms, the compute problems, right? Machine learning. And finally, at the level of systems, science, computer systems. How can we actually build something inspired by this, much different from what we do today, and actually thereby solve a new complexity class of problems? Okay, so I'll discuss all three of these, and in each case I'll have one in-depth example, and it's just so that I'm sure there's some of you who probably would love to see things a little bit deeper. But otherwise, I'll mostly be at higher level. So let's start with the middle one, the computer science part of the algorithms, right? Like I love that quote that do things that don't scale. So primarily, we are focused here on those algorithms, right? The ones that today do not scale. And how do we make them scale? So that we can deal with the data and the rate at which compute is being offered by technology. So deep learning gets a lot of press these days. Why? I'm not going to go into tutorial explanation for this, but let me note a few things. The most important thing here is that it learns on its own a deeper representation of an object. Okay? Deeper part is very important. That's why it's called deep learning. And it learns on its own is the most important part, because what is really excitement about its success is that it is finally, for the first time, automating or the feature extraction part. We have not solved the unsupervised learning problem yet. We still need supervision. But the supervision needed, the labeling needed, is not one of experts, but you and I. 150 countries, unemployed people can look at the images and call them cat, dog, just label them. It's very easy, that part. It's much harder to count on experts who can tell you what makes a cat a cat. Okay? That's what we are counting on so far. We are counting on experts so far. That's why these systems are called expert systems. Experts are not even born once a century, right? And how do they think? How did Newton even think of gravitation by an apple fall? Who knows? It's very super complex. So we are now more reliant on expert is the biggest reason for excitement. That's what deep learning does. It automatically finds the important features, and by only counting on non-experts to label the data, or sometimes just by watching them. That's the primary reason for excitement. But you and I should still be curious as to why this works. What are the theoretical reasons for it to work? The theoretical underpinnings are not quite there yet, just to be very clear. Mostly what we have learned is statistical recognition, statistical pattern recognition, which is good enough for mining, but if you actually want to synthesize things or simulate or predict, you need a generative model, a model that can predict, right? Because they are called generative models because it gives you godlike ability to synthesize something, to create something. We are not quite there yet. We are mostly talking statistical pattern recognition. But still, it's exciting because it can actually automate feature extraction. So let's understand the reasons why it works. It's known, and I have some results here that you can look up, that it's a very old theorem, which is the most fundamental theorem for deep learning, is that complex functions, first of all we are talking about in this case are complex functions. What makes the function complex? It's rapidly changing, number one. Number two, non-convex. Rapidly changing function. That's what we're trying to learn. Something here or stock market doesn't matter, right? What makes that hard? A complex function, if you are forced to represent it in k layers, you need exponential number of compute units, the nodes. But if you add one more layer, the amount of compute goes down and becomes polynomial. That's the most fundamental result, which tells you that a deeper representation is more compute efficient representation. Intuitively, you can imagine trying to do all forms of logic gate in one level of logic by encoding the truth table. But then truth tables are 2 raised to 4, 2 raised to 8. They grow very rapidly. But if you can do that, since we do not have exponential compute, we need deeper representation. What was the problem with that? You could not train and learn the deeper representation. We never had enough data to learn the deeper representation. That's what we now have. To the extent it works, it works. But that training itself, theoretically, is NP-hard problem. We do not have exponential compute. So how are we doing it? There are some new results that are coming up which actually show that under certain conditions of sparsity and on both input and the weights, the problem is not NP-hard but more polynomially tractable. Those are new results. All it means that in real world, probably the weights and the inputs do have non-random distributions. There is some pattern. That's what makes this problem tractable. Now, theoretical results aside, its working is the most exciting thing. So let's look at now a hard problem in there. And now this is one of my deep dive. I'll quickly flip through some foils. So one of the hard problem is looking at the output layer. We have, in most real world problem, the output has many, many items in there. Just imagine the number of objects in the world. It's not just 1,000 objects like ImageNet. There are probably millions. Even there are very many kinds of vegetables, there are very many kinds of people, there are very many kinds of words in a vocabulary, roughly a million. What we are solving today are only toy problems, right? When only 1,000 classes or few classes can be detected. And we do that by creating something called fully connected layer, which is where the complexity comes. So we are learning, and we have new research now, which we just published, which is about coming up with a new sampling function so that you can actually sample the output layer. If you cannot deal with that output layer, the problem is not scalable. The current approaches to deep learning are not scalable. So what we have done is we have focused on, like you see, that function, right? That in a given state, you come up with a new sampling function so that you can actually subsample the output layer. Now, the details are in here. The challenge again becomes, how do you multiply skewed matrices, which high performance computing has ignored for a long time, meaning very large dimension on one side and small dimension on the other side. Such matrices, very small kernels for convolution, 1 by 1, 2 by 2. These are the things which are not done by machines very efficiently today. If we do those things and a new novel way to sample, right, the net result was that we were able to actually achieve very significant performance for a problem which is non-trivial, namely the NLP problem, meaning given a word, you're trying to predict the next word. And sometimes, remember, you have to look at the entire sentence or the entire paragraph, entire page to get the context of that word, the meaning of that word. That's why we picked this problem, which is a non-convolutional neural network, something where a time dependency exists. You need a lot of context, which is true for most of our problems. In fact, the model is called long and short-term memory, where you brain things like that. It has some time component in it. By solving this problem, by understanding this problem through a new sampling, right, like I said, we were able to scale it. We were able to scale it, and again, I am skipping the details, but the scaling you can see here, that's something which was very hard. We are now able to solve this problem in matter of days. This problem traditionally would have taken us more than many months of training, okay? But even with 64,000 word vocabulary, the real vocabularies are million words. We are able to bring down that many months of training by scaling it, and in fact, with unoptimized code, it was probably close to a year. So that year is going down to months, is going down to days, as you can see here, is because of the innovations at all levels, right? And some cases we are doing much better than the best results on some GPU, CPU. GPU, CPU is not the problem. It's the algorithm. Like I always said, the 1000x speed up or 100x speed up happens at the algorithms level. After that, you only lose. You pray that you lose less and less at compilers and machine level. But algorithms is where 100x speed ups happen. So I like that last speaker's suggestion that algorithms should be taught very, very early on in schools. So moving on, we didn't stop there. We are now looking at even harder problems which are not neural network problems, which are not constrained by the constraints of neural networks, which from this stage to this stage to this stage, but more general purpose networks. The networks which actually give you the power of being able to explain, right, being able to generate, right, the Bayesian problems. Now, in this case, we signed up for a challenge from NSF for a plant, right? It's a plant, and the data given is microarray, meaning all the genes of the plant and how the behavior of those genes, right? What happened. And you're trying to reverse engineer the gene regulatory network, which is a very complex network. And imagine, this is very similar, analogous to if you're given a data on who's calling whom, and you're trying to reverse engineer a social network, right? So it's the same kind of a problem. Now, anyone can be friends with anyone. Any 2 or 3 or any number of genes can together form a network to control a feature that we see on a human, right? So this is a very hard problem. For the first time, we were able to solve this problem at the scale of number of genes, tens of thousands. And we were able to reconstruct the gene regulatory network of this plant by going on a machine, which was #1 supercomputer, the machine in China, right, Tianhe supercomputer. So by that amount of compute, but the good part is we are able to solve a Bayesian inferencing problem at the level of tens of thousands of nodes. And the net was, and this would have taken 27 years. We were able to do it in 8.5 minutes. That's the power of compute we're talking about. If you do the algorithm part right and you're able to apply these today's machines and today's compute technology, we're able to do them in real time. Now the net is that in this case, how do you know that you've done the right thing? What we did then, we concluded some new genes which are responsible for a plant function. Now in this case, you can actually order seeds of a plant which certain genes knocked out, almost like the Mendelian experiment. We did that experiment to convince ourselves that we actually discovered the right new genes, part of a new gene regulator network for a plant feature. Now this is how I'm suggesting, or I'm hypothesizing that science will be done, not in the wet lab, but driven largely by machines being in the lead and actually guiding you, where then the lab work, the scientist's work is minimized to only focus on certain genes or certain synthetic materials, synthetic plant, drug design, if we are able to do these things at this scale. So moving on, now let's talk about the other part, the neuroscience part, right? So how do we really still understand the most complex regulatory network right here? Now we're not talking 15,000 genes, we're talking 100 billion neurons. We have signed up to do that too. We are trying to understand how they work, how they interact, how they encode things. The encoding here is the crux of the whole problem. It's a very sparse representation, right? So the key here, this is not our observation, this is a work that we have signed up for 5-year collaboration with Princeton, the same person, Daniel Kahneman School, right? Where we are focusing on attention. Attention is the key. That's what mind is. You may all be looking at me, listening to me, still may be thinking your grandma. So what you're thinking may be very different than what you're looking, because you may be in an attentional state which is completely blocking what I'm saying. This guy talks too fast. I don't understand what he's saying. Let me start thinking, what am I going to do tonight, right? So if I know what the attentional state you're in, I can really figure out much sooner or much easier which neurons are firing. Without that, it's a huge state space. That's what we did in the plant case. By Bayesian approach, by conditioning it, we were able to cut down the state space dramatically. That same conditioning here, the condition is coming from the state you're in. I'll give a very simple example. If you're trying to reverse engineer what a chip may be doing, there are billions of transistors. But if you know that the chip can ultimately only execute some hundreds of instructions. So if you know the instruction it's executing, the load or a store, you can literally trace the path. Only few transistors are active. Rest of the billions have no role. Same thing here. If I know the state you're in, I have a much easier time monitoring and predicting what you're thinking. And otherwise, it's a hopeless task. So that's what we're doing. We believe that there are only finite number of attentional states that a human brain has, they call mind. Can we discover those? Can we reverse engineer those? So this is the collaboration we have signed up with Princeton. And this is for the first time in there, psychologists and neurologists are in one building. This is the point I was trying to make. Even these academic disciplines have not worked together. Psychologists live in their own world, and neurologists live in their own world. For the first time, they have joined forces, and now they found a compute problem. That whole loop takes 60 hours. We need to happen in seconds, so that while the guy is in fMRI, you can actually decode and do causality on the correlations we are seeing on the large amount of data. So what we have done here, our goal is that in over the next 5 years, we have I'll quickly go through it. Our goal is to be able to decode more than 100 attentional states of the brain. If we can do that, what can we accomplish? It'd be something like this. You'll have a Jeopardy-like game, but machine is simply showing video of what you're thinking, not what you're talking, not what you're doing. You can imagine the power of this. How? By actually knowing the state you're in, which makes this problem much more computationally tractable. Okay, it's similar to the mind reading exercises that Tom Mitchell and all did few years back, but that was only limited to 10 images, right? So moving on, I'll just show you again 1 or 2 results. We have now able to collect large amount of data, which they are collecting from animal experiments or human experiments. They have the right approvals to do that. We are aligning those images so that across multiple subjects, this is a very difficult thing to align. So even across people, these things differ. So you have to properly align them. That's how we get large amount of data. Because one individual does not give you enough data. So with large amount of data across multi-subjects, we now are doing topographical analysis. So I earlier did deep learning, then I did Bayesian inferencing. Now the third class of algorithms, topology. right? So topological problems we are discovering, we believe that there are only few centers, few topological entities here, we are discovering them through topographical analysis to see can we really find those centers of attention, right? So we are looking at, in this case, we have sped up 2 different algorithms by more than, as you can see, 100-fold, 1,000-fold. I'm not here to brag speed up. All I'm here to tell you is that these techniques for these neurologists and psychologists are now finally happening in real time. We are taking less than 3 minutes or less than 17 minutes per iteration. All it means they can real-time experiment. This is what takes correlation and brings causality, so that you can truly discover what is causing what, and how exactly, which state I'm in, and how do people think, how is information encoded, what are the basic primitives, what's the instruction set of human brain, just like the instruction set of a processor, right? Moving on, we believe that we also have at least some understanding of these machines, and that's how we're building new machines, new silicon, which is a non-von Neumann machine, meaning it has no distinction of program and memory. It is actually blurring all those distinctions, and this is, I'll skip this, but this is what's called neuromorphic computing, right? And in neuromorphic computing, our focus is to actually build a chip, right? A chip that is very different from von Neumann computing machines, which will be focused on very small kernels, but these kernels will actually give us 100-fold efficiency, energy efficiency. We are doing primarily CMOS. We are also incorporating some non-CMOS, emerging nano oscillator, and some new technology, non-CMOS technologies in this to actually build a chip with 100x more efficiency. So I'll quickly go through this, and I'll skip the details. Just essential important point is that we are actually building a silicon where we believe we can get 100x efficiency at the level of these very core kernels, not a full computer, but a core kernel, so that this could be an accelerator for the traditional machines, and for simple things like, can we actually do some pattern matching problem, constraint satisfaction problem, and deliver 100x efficiency, energy efficiency. That's what this one does. Now just let's note one piece of data. This roughly, you take roughly 4 or 5 gigaops per watt is what the efficiency of this is. That's how you are able to do for 20 watt, however many billion operations here. Today's machines are also roughly at the same level, 4.5 gigaflops per watt. So we are roughly at the same energy efficiency level. What's the biggest reason why we don't have this kind of compute problem? Because our interconnect architecture is very different. We spend enormous amount communicating as opposed to computing. Brain, each neuron is connected to 10,000 other neurons. We don't build such chips. Our one node of a machine is barely connected to three or 4 other nodes. High radix networks are very, very difficult. Here, each one is connected to 10,000. That's the kind of new interconnect, new machines we're talking about. Very different architecture, very different programming. You send 10,000 messages, only some of them will make it, but you can reach 10,000 neighbors in one hop. Okay, so let me now try to sum up. What is happening is that we are at an unprecedented convergence of massive compute with massive data. And this will fundamentally change how we have done computing and what computing has done for us. It takes computing a new realm of applications which are so far completely untouched by Moore's law. Okay, these are basically social problems, efficiency, inefficient ways of solving problems, like in farming, like in teaching, like in health, like in transportation. And that's what we are now will finally get there. We'll finally have enough flops. I often say that when scientific problems end with exaflops, the mom and pop problems begin. This is a typical myth that we need a lot of compute for what? For weather prediction, who needs that? In fact, the mom and pop problems, the mundane simple problems is where that exaflops are minimum requirement, and then begin after that. So let me give the same example that was earlier chosen. For example, you can then tackle a real problem of farming, right? How do you improve crop yield? It's not a million parameter problem. Our typical ImageNet deep learning challenges are roughly tens of million parameters. If you look at a simple problem of how to improve a crop yield in a single season, single crop, single country, trillion plus parameters. So if you can solve this problem through deep learning, which is what we hope to be able to do in a matter of 2-3 years, trillion parameter, less than hour of training time for complex neural network topologies. What it will let us do is it will let us challenge and solve such problems where all you're trying to do is improve the crop yield by 1%, which is almost like doubling it, 1.2 to 2.4% yield growth okay, for cereal crops, so that you can simply feed enough people by 2050. Nothing more than that. Just to be able to feed the population growth, you need to be able to improve the crop yields by that small percent. But it's a very, very complex problem. We are hoping to be able to apply computing to such problems: synthetic materials, synthetic drugs, new ways of improving yield. Thank you. That's pretty much my summary. This is the first time we can actually take supercomputing to the masses directly, right? It's almost like scientists or compute guys went to God and said, can we think of some problem where masses ask for lots of compute, exaflop of compute, and not just some scientist for weather prediction or material science? And God thought and said, okay, let there be compute. And that's what this deep learning is. It's let there be compute like problem, because it's a real-time loop, because there's no perfect teacher, there's no perfect training. So training keeps happening. And once you train the model, it's a very compact model, you ship it to the phone. And there's no perfect training. You keep learning more and more. It's a lifelong learning, like the last speaker said. Machines and humans will both be in school, lifelong learning, and probably when unsupervised. We don't even go to school. You just show up on the street and you learn real time and lifelong. And that's what this enables. It's the first time we can see supercomputing to edge devices back to supercomputing, because there are billions of edge devices. Data comes back, training happens, new model goes. Improved training happens, new model goes. It's a lifelong process. Thank you.
Okay. Dr. Dubey, thank you for the very intriguing lecture. 예, 강연을 들으면서 you can come and sit here. 강연을 들으면서 주목할 만한 내용이 많았던 것 같습니다. 먼저 방적 공장인 밀즈가 1차 산업혁명의 시작이었다면 4차 산업혁명 시대에는 또 다른 밀즈, 머신 인텔리전스 레드 서비스가 새로운 변화를 주도할 것이라는 이야기는 매우 흥미로웠습니다. 또한 인간의 뇌 구조를 모사한 Neuromorphic Computing이 인간의 도움 없이 스스로의 학습을 통해 그동안의 난제들을 효율적으로 해결할 수 있다는 점에서 인간의 사고 능력과 두뇌가 가진 무한한 가능성을 확인시켜 주셨습니다. 컴퓨터가 과거 넘버 크런처의 기능에서 벗어나 현재 레코멘더의 역할을 하고 있으며 앞으로는 스스로 지능을 가지는 디시전 메이커로 진화할 것이라는 점 역시 매우 인상 깊었습니다. 그러면 플로어를 대신해서 제가 먼저 몇 가지 질문을 하도록 하겠습니다. 질문은 제가 예의상 그냥 영어로 하겠습니다. Okay, currently many multinational corporations like Google, IBM, Facebook, and Intel are aggressively jumping into AI-related technology development. In your perspective, what level of development does AI stand today, and what are Intel's strong points in this field?
Yes, our primary distinction is technology. So our goal is to make, like I said earlier, make these things scale and make them delivered at the cost and efficiency that most people can afford. So our primary goal here is to deliver the technology so that you can actually scale these algorithms and deliver them. How do you deliver supercomputing to masses? And that's where Intel comes in. That's how we are different from all of them. We want to help them all.
Okay, thank you. Now we anticipate that the future of human lives change with the development of AI that is able to replace most of what are considered people's job. Is there any representative example of change in the future human society due to the advancement of AI?
Yes, so two things. One, like I said, it takes computing into a realm of new applications, applications which are social applications, problems which are social problems. For the first time, computing will begin to tackle those. and society is operating at a level far below desired in all those areas: health, transportation, farming, name it. So there's a dire need to improve efficiency in those areas. And that's what this will let computing do. Computing will finally actually play a role where it matters, where society desperately needs. What it means for people like us individually is that it actually lets you focus on things that you are very good at, things that you really like, as opposed to just mundane learning, engineering, medical, whatever. That's, like I said, there's a huge difference between the best and the worst in any human endeavor. This lets you focus on things that you're really much better than average. Why? Because you have some real skill. And you don't have to look at things where you're really hardly good. So each one of us will then get to focus on things that we really enjoy, things that we're really good at. And machines are not going to be able to take over you in those domains anytime soon. So that's, I think, is the implications for us.
Okay, thank you. Then how will the advancement of AI technology innovate the development of science and technology? For instance, National Research Foundation of Korea is an R&D funding agency which support diverse area of basic science. Then for the future development of AI in Korea, especially which area of basic research should be strengthened first, you think?
Yes, I'll go with, also repeat what the last speaker said. There's a big need for bringing quote-unquote computational literacy. Now I'm talking about a higher level of computational literacy, namely in how do you deal with huge amount of data, huge amount of compute, right? And these people, I'm talking about that kind of literacy for people in different domains: musicians, health professionals, scientists, right? How do you make them computing aware? They generally do math level programming. How do you actually make them computing aware so that they can benefit from and actually process and deliver and learn insights? So the teaching of computing needs to become essential in all disciplines, starting from undergraduates, starting from schools, and all the way to even graduate schools, and especially in the science part of computer science needs to be taught differently, but needs to be taught.
Okay.
And it'll let us solve problems, like I said, which so far have been out of reach for computing. In how do you do better chemistry, better material science, better design of a strategy.
오케이. 시간이 이제 얼마 남지 않았는데요. 오디언스부터 들어온 질문을 좀 드리겠습니다. 한글로 할 테니까 you better. 연료 없이 에너지를 ready? Yes. 연료 없이 에너지를 출력하는 연구기관 퍼페추어 엔진을 출연 불가능한 것으로 알고 있습니다. 앞으로도 불가능할까요? 바이컴 ENG 김정용님께서 질문하셨는데, you want me to repeat?
It didn't translate.
It's okay.
I couldn't.
You didn't hear?
No, I didn't hear.
You have to
Hello.
channel 2.
Oh, yes.
You said to channel 2.
Oh, sorry, one more
Okay,
time.
I'll do it again. Yes. Channel 1 is
One more time.
English. Yes. Okay. 연료 없이 에너지를 출력하는 연구기관 퍼페추어 엔진은 출연 불가능한 것으로 알고 있습니다. 앞으로도 불가능할까요?
I don't think so. Yes. We won't violate any principles of physics in this whole thing.
아마도 우리 듀베이 박사님 밑에 답할 그런 전공의 분야의 질문이 아닌 것 같습니다. 다음 질문하겠습니다. 기계가 의사결정을 했을 경우에 그에 따른 책임, 문제가 발생했을 경우에 그 책임은 누가 어떻게 질 것일까요?
Yes, that's a very good question. Who should be held accountable? And this is again a legal, ethical matter, right, which is being hotly debated. And there was a recent change in some states. Law changed where if your car is self-parking itself and something bad happens, it hits the car owner is responsible, not the car manufacturer. Now, such changes will probably take place many places. The bottom line is, if the self-driving car is safer than humanly driven cars, those cars will be on the road, right? They'll never be perfect. They'll still make mistakes. And who is responsible in those cases? It's again beyond my expertise, but it's being debated hotly. And let's see. At least some states are now passing or making the owner responsible as opposed to the manufacturer.
오케이. 답이 되셨을까요? 예. 사실 이 지난 세상을 떠들썩하게 하고 우리나라도 떠들썩하게 했던 알파고의 승리는 아마도 이런 하이 컴퓨팅 파워의 도움 없이는 이루어질 수 없었다고 생각합니다. 그런 하이 컴퓨팅 파워를 만들어내는데 오늘 여기 오신 듀베이 박사가 근무하는 인텔의 컨트리뷰션도 컸을 거고, 그 일부에는 우리 삼성전자 같은 반도체 기술의 발전도 이득을 담당했다고 생각합니다. 그래서 앞으로의 이런 인공지능 시대가 열리는 4차 산업혁명 시대에 우리가 이런 강연을 통해서 좀 더 우리가 빠르게 좀 적절하게 우리나라가 준비할 수 있는 그런 계기가 되었으면 합니다. 오늘 첫 번째 특강 이걸로 마치겠습니다. Thank you. 감사합니다.
Thank you.
네, 오늘 첫 번째 강연을 펼쳐주신 프라디 듀베이 소장님, 그리고 정민근 이사장님께 다시 한번 큰 박수 부탁드립니다. 네, 오늘 좋은 말씀 많이 들려주셔서 대단히 감사드리고요. 네, 수고 많으셨습니다. 자, 이것으로서 첫 번째 특별 강연 순서 마치도록 하겠습니다. 잠시 휴식 시간 갖고 저희가 두 번째 특별 강연 이어갈 텐데요. 이 자리에서 10분 뒤에 저희가 바로 두 번째 특별 강연 시작하도록 하겠습니다. 조금만 쉬고 다시 만나 뵙겠습니다.